Hey robot makers, hope you're having a good day so far. So do you want to learn the differences between Rust and MicroPython and how they would compete head to head? Then this is the show for you. So let's dive straight in. My name is Kevin, come with me as we build robots, bring them to life with code and have a whole load of fun along the way. Okay, let me get over to my slides. We'll make a quick start and then we'll have some fun with some code. So yes, today's show is all about Rust and MicroPython. You might not have heard of Rust, hopefully you have, and it's a newish programming language, and it's very specific for making very fast code, a very safe code as well. When I say it's as fast as C is what people are claiming out there. We've heard of MicroPython before. I've covered this an awful lot on the channel, so I'm very keen to see, does Rust is it as good as MicroPython? Is it better? How does it compare? So MicroPython is a lean and efficient implementation of Python 3, and it's designed for microcontrollers in a constrained environment, usually running on microcontrollers. Look around to see if I've got a microcontroller to show you, such as this Raspberry Pi Pico here. So we're going to have a bit of a head-to-head smackdown between these two. So first of all, let's just have a quick talk about generations of languages. I've just pressed that mute button. I don't know how many times that it hasn't taken. So generations of programming languages. So there are approximately 5 generations of programming languages. The very first ones were just pure machine code. So back in the 40s and 50s, people were building great big pieces of iron computers at the very, very beginning. And yeah, you had to program them basically bit by bit with machine code. So you would punch cards, this would be fed into the machine, it would then read in the code and run the program. The next step then was assembly language. So this is kind of a symbolic language. You've got little 3 or 4 character little symbols like move, and then you would have some parameters like move the value 7 into memory address, 1, 2, 3. And assembly language really made it a lot easier than machine code, because machine code is simply ones and zeros, or at best octal or hexadecimal code, whereas assembly language is a bit more like English, and you could even have comments and things in there and reusable code segments. You wouldn't have to put in every single piece of code one at a time. You could have reusable code blocks in there as well. Next was the 3rd generation languages. These were things like Fortran and COBOL. Now back in the day I actually did learn COBOL for 2 years at university. That's the Common Business Oriented Language, I think it's called, and it's used quite a lot in banks and things. It's very, very structured, and yeah, that was one of the very earlier languages that was adopted. Fortran was used in universities a lot for doing sort of financial or numeric type applications. Next up then we had, and also mentioned there, that C is also a 3rd generation language. 4th generation languages came along in the sort of early 70s. Things like SQL, although you might argue that's not a true programming language, it is a language. And we have other 4th generation languages such as C++, Java, the Arduino processing language, and even MicroPython and Rust are technically 4th generation languages. And then in the sort of 80s, we had the beginnings of 5th generation languages, such as languages that could do I can't even pronounce it, logic programming and AI. So Python is one of the leaders in this kind of environment, because you can do things like ChatGPT in Python. There's lots of extensive libraries out there for doing AI-based neural network programming, like TensorFlow and things like that. So they're kind of 5th generation languages. And the generations it's a heuristic rather than absolute thing. So if you're coming at me in the comments to say no, MicroPython's a 5th generation or Rust is a 5th, these are heuristic. There tends to be a set of rules that define what the languages are, and also the kind of time period. So you could argue things like ChatGPT, are they 6th generation languages? If code creates code, is that 6th generation? So AI generated, but there isn't actually any generations that have been specified, certainly not on Wikipedia anyway, to sort of define what these are. So I just wanted to put that in context there. You can also see the kind of time period we're talking about. So Python sort of early to mid 90s, Java is sort of late 90s, the Arduino processing language sort of 2005-ish onwards, Rust We'll get to that shortly, but you can see 2010s MicroPython slightly later than Rust, so you can see the kind of maturity of some of these languages as well. Obviously, that's not every language that's out there. So let's talk about Rust for a second. So Rust began as a personal project by Graydon Hoare. Is it Hoare? Hoare? I'm not pronouncing that correct, probably. In 2006. Mozilla sponsored it. So Mozilla, who did the web browser Netscape, they sponsored this in 2009, and it was announced in 2010. And then the first stable release usually takes quite a while. You can see 5 years later, May 15th, 2015, first version of Rust was announced and released. So the name Rust is a play on words related to rust fungus, which is a parasite that grows on fast distributed systems, and a nod to the speed and concurrency aims of the language as well. So Rust is, the idea is you can use a lot of the cores. If you think about how architecture has changed over the past 50 years in computing, we now have multiple cores. Even your mobile phone will have multiple cores on there. So Rust kind of natively takes care of these. Then we have lovely MicroPython, of course. So I'll put my biases out there. I absolutely love MicroPython. It's going to take a lot to tear me away from this, and there's a number of reasons that we'll get into today why that is. So MicroPython was created by Damien George as part of a Kickstarter campaign in 2013, and the project was developed to make a lean and efficient version re-implementation of Python 3 language for microcontrollers and constrained systems. So that was specifically designed for microcontrollers. The first couple of releases, MicroPython from 2014, and then it continued on from there till today, so 10 years later. And MicroPython just reflects the language's design goals of being a small, concise version of Python suitable for microcontrollers and other low resource systems. So it's specifically with that in mind. It's an interpreted language, whereas Rust is a compiled language. We can talk about that as well a bit further on. So language design philosophy. So Rust emphasizes zero cost abstractions. What does that mean? We'll get into that. Memory safety without garbage collection, and type safety. So one of the things off the bat, I would say Rust is quite an advanced language. So if you're a beginner, it's probably not an easier language to learn as your very first language. Something like MicroPython or Python is a lot easier to comprehend. There's a lot less kind of cruft around the language. We'll see that when we get into actually writing some code. Whereas Rust kind of is, if you've learnt C and C++ or Arduino, Rust will be a lot easier to understand because you'll already have a lot of that knowledge coming to Rust. So it's probably a better as a second language to learn, I would say. And things like this zero cost abstractions, that will make a lot more sense if you've used something like C++ in an object-oriented way. Memory safety is to do with if you create a variable or an object in memory, something has to take care of that. Something has to know how many things are referenced in that piece of that variable or that object in memory. And if you don't manage that correctly, you can leave that orphaned, and that means that you've got memory leakage. And over time, the memory leakage will be to an extent that it runs out of RAM on whatever it is you're developing. Now, if that's developing something for robotics and you're on a constrained system like a Pico or an ESP32 or a Feather, you'll run out of memory pretty quickly on that. So memory safety is quite an important thing. Now MicroPython takes care of that for you. The sort of counter to that is MicroPython, with it being Python based, has this global interlock, which is a kind of constraint, and really you can only run one thread at a time. Even though we can do multi-threading, in effect we're only really running one thing at a time on there. So Python kind of helps you, but it kind of gets in the way as well, whereas Rust doesn't have those kinds of problems, and it's running very, very fast because it's machine code, whereas MicroPython is interpreted. So MicroPython aims to be as compatible with the Python standard as possible, so you can bring all that knowledge from Python that you have and use it on MicroPython, so there's no extra quirks really to learn on that, other than if you're using hardware, general purpose IOs and things like that, you just need to learn those specific things. And there's a focus on simplicity and efficiency. And that's the thing that I love about MicroPython, is it's very, very quick to develop in, and it's very quick to get running on your processor. The code itself may run a lot slower, maybe 10 times slower than Rust code, but maybe that isn't an issue for what you're doing. So if we're doing robotics, say I'm working on this robot arm, I'll give you an update on in a minute, and I want to position this the stepper motor How often do I need to update that? Is it like fractions of nanosecond, or is it every half second? And the difference in speed updates there might make a difference between whether you develop something in Rust or develop it in MicroPython, for example. But I've never found a use case yet where MicroPython is too slow for any kind of robotics projects. Again, let me know in the comments if you think I'm wrong there, if you think there is certain things, maybe a balancing robot, you need to have that kind of level of speed. And have you actually tried that in MicroPython yourself? And come up against a barrier. I'd be very interested to know what the real world use cases are where you think Rust is better than MicroPython. So I've got a note there about comparing the design goals and how they influence the language features. So Rust, I would say, is an evolution of C. It's very C-like in how you program it, and we will do some programming in a minute or two. So if you're coming from C, C++ background or Arduino, Rust will kind of make sense to you. And it's a lot safer. So the code that you generate is more likely to run once you've got rid of any bugs in there. So there's a lot more effort put into making things type safe. So if you have like an integer, for example, you can't use a floating point number. The compiler will basically just say this is incompatible. In Python, it's like it's an object, you can store whatever you like in there, it's fine. But that could potentially lead to code problems later on. So Rust is very safe from a development point of view. What you write will work. MicroPython is just very, very chill and relaxed. It'll let you do whatever you want, but there are consequences to that might mean that you've got bugs in your code that you can't easily debug. So let's have a look at performance and efficiency. So Rust is compile time. It has compile time, memory and type management. So that means that it will, like I said, detect problems in your code before it's even finished compiling so that you can fix those and get code that works the way you intend it to. Lots of features of Rust are designed to reduce down any of these kind of memory type leakage errors that you might get. And that's very common in computing. Certainly with C and Arduino type programs, you can create objects and then not get rid of them properly, and then you get memory leakage, and over time that will cause problems. Your chip might reboot and you might just see a pause for a second as it starts running the code again. Rust will get rid of all those kinds of issues. MicroPython is an interpreted language, so it's obviously a bit slower. There's an overhead that the fact you have to have the interpreter installed on the device that you're using. So that does take up a bit of memory and also runtime. But it's optimized for very quick and easy to program on microcontrollers. So one of the main reasons I love MicroPython is just how quickly you can write a program, how simply that looks as a piece of code, and how quickly that can actually be up and running on a microcontroller. And with tools like Thonny, you can develop in Thonny and actually run the code as you're developing it. Whereas with Rust, you have to write your code, compile the code. Once the code is compiled, you then have to load that onto your Pico, and that might involve many different steps. We'll have a look at how we can do that later on. Not as a demonstration, but kind of as an in theory, because I've actually not been able to get that to work yet. It's quite complicated to do. And I think the tooling around MicroPython is a lot more designed for getting you up and running, getting code running on microcontrollers than Rust, which is kind of a general. It can run on big servers, it can run on embedded devices. It's kind of a bit all over the place, whereas MicroPython is like specifically for embedded devices. So I would say in that case, MicroPython wins. But from an execution point of view, Rust is going to be quicker. So development and environment tools. So again, this is where I think MicroPython would win, because we have things like Thonny, which means you can develop code and run it at the same time on the microcontroller. You can debug the code on the microcontroller, and at no point is that tool that you're using taking you away from getting the answers and getting the code up and running. Rust is a kind of traditional development process. So you write some code, you then stick it through your compiler. You can also build out using a tool called Cargo. We'll have a look at Cargo in a minute. That's a package manager. It's kind of a bit of an everything. It can grab all the dependencies that your code might need, compile them in, link them in, and then generate the output. And then we need some way of getting that compile code onto your microcontroller. So unlike MicroPython, which has it kind of shows up as a file system when you plug it into a computer, you're not going to get that with a microcontroller that's going to run Rust code. It's more like when you have an Arduino and you plug it in, you've got to compile and upload. It's very similar to that. But there isn't a tool out there currently like the Arduino IDE interface for Rust. So I kind of think they're missing that for microcontrollers. Now there is this Rust Up toolchain manager, and what that will do is just make sure your entire Rust environment is up to date. You can simply just do Rust Up and update your entire environment. The Cargo will also do all the dependency management for things that you bring into your code. So any kind of modules, the version management of all that is managed by Cargo. It's pretty cool. I know that there's been quite a lot of work in the Python environment to try and bring it up to the standard of Cargo, because it's like a really, really neat tool. But in MicroPython, we've got the REPL, this read, evaluate, print loop command line that you can, when you plug in a Pico device, you flash MicroPython onto it, you can then interact with the microcontroller directly. And then we've got tools like Thonny, Visual Studio Code, Move. There's quite a lot of different ones. Even the Arduino have a tool, actually. I'll fire that up because I was meaning to show this. I think last time I was talking about Arduinos and ESP32s, I think. So Arduino have actually developed this Arduino lab for MicroPython, so you can develop MicroPython using an Arduino tool. So that's pretty cool that they've developed their own. There's like a very simple connect button, run, stop, reset, save your code. You can have like a console, the terminal that pops up. You can also look at your files as well. So they made this very, very simple environment for working with MicroPython. So that's really cool that they've done that. But they are an embedded device manufacturer, so I guess that's in their wheelhouse. Now with MicroPython, we've got the limited standard library. So if you think Python is like the full-blown version, MicroPython is a subset of that, and it doesn't have every single feature of the full MicroPython, the full Python 3, but it's got more than enough to get you up and running to do a lot of things that we do in robotics. And we also have UPIP, I think it's now just called pip, which is the package manager, so we can grab if we have an internet connection on our microcontroller, we can grab libraries live off the web and use it on our code. So I would say the MicroPython environment is very mature, specifically for robotics and embedded devices, whereas Rust is more of a traditional desktop and server-based application environment. So I think MicroPython wins that one as well. I'm not biased. Memory management wise, so Rust has this really interesting ownership model. It's also got this borrowing. We can have a look at that perhaps in the code in a minute. And lifetimes for compile time memory safety. Again, these features are all designed around making sure that your code is really robust and doesn't introduce memory leaks and issues to do with memory management. So this ownership model is about if you think about when you write a piece of code and you create a variable, who owns that variable and who's looking after that variable's life cycle? So this lifetimes ensures that if you assign that variable a number, a value of any kind, once you finish with that, what happens to that memory? How does it get deallocated? Python takes care of all that for us. We can manage with the garbage collector that's in there. Rust doesn't have a garbage collection because it has these different ways of managing it instead. The idea of borrowing is quite interesting. So you can have a variable, say you've got like X for a location on a screen, and you want to borrow that value that's in that variable. You can actually do that in your code, and you can add extra parameters or extra attributes, I should say, to that variable. So you might give it like a width or a height, for example, and it doesn't affect the original variable. You can just add these attributes to it by borrowing from it. So there's all these extra features in Rust there to do with memory management, which is pretty cool and very useful on microcontrollers because we haven't got very much RAM to begin with. Whereas MicroPython has garbage collection. There's a part of the interpreter every now and again. It will just check to see, do we need to get rid of any memory? Do we need to like reallocate it to something else when something goes out of scope? And some of these concepts are quite intermediate to advanced skill, I would say. If you've never understood what garbage collection is in MicroPython, well, that's the beauty of it. You don't need to know about it. It just takes care of it. But essentially what happens is, as your program is running and it's assigning variables, values, and then deallocating them, you don't even have to worry about that deallocation. Python takes care of that for you. And the garbage collection is essentially just keeping the table of what variables are in memory and how big they are and so on. So when you request space for a new variable in memory, it takes care of all that for you without direct user intervention, as it says there. So there's kind of like MicroPython takes care of things for you. There's an overhead with that in runtime, and also the use of memory. It takes memory to use memory, if you like, in MicroPython, whereas in Rust, the way that the system is designed from a compile point of view means that you don't have to worry about garbage collection. It's kind of built into how these objects are created. Now there is an overhead with that as well, and we'll see that when I'm going to write 3 programs in a minute, one in MicroPython, one in Rust, and one in C, and we're going to compare the different sizes of the outputs of each of them to see how efficient they actually are. We'll do that actually on the Mac rather than on a microcontroller. So let's have a look at use cases and application areas. So Rust is ideal for systems programming, WebAssembly, embedded devices, and high-performance applications. So again, efficiency and reliability is key for Rust. It's designed to be the sort of future, the current and the future way of writing programs. A lot of people that love Rust are really, really fanatical about their love of Rust, and that's because of the extra features that brings over languages like C and Java. Whereas MicroPython is suited for microcontroller programming, Internet of Things, and educational purposes. And I wouldn't say, some people sort of say it's like a toy language because Python is a scripting language, and I would completely disagree with that. Just because it's simple doesn't make it less useful or not proper or not professional. Python is used in industry all over the place. Things like ChatGPT programmed in Python, and there's a lot of products out there that are based on MicroPython as well. So it's definitely a growing language there. So I would say MicroPython is definitely suited towards education and getting people up and running, but that simplicity extends to experts as well, because they can just get on with the complex task of whatever it is they're doing without worrying about the language getting in the way. Yeah, Adam, we're not going to talk about Java today. Obviously Python would win, hands down. Let's talk about community and support then. So Rust has got a growing community, extensive documentation. It is very good, to be honest, the documentation there. They've got quite a lot of active forums and corporate support. So we'll have a look at the website in a minute when we go to the demo. MicroPython also has a very strong community, and particularly around the embedded and educational sectors, and there's lots of resources and tutorials online. Quite a few I've created myself on there, but the community around MicroPython cannot be understated. When I started writing MicroPython code, I didn't know any of the people behind it, and very quickly they got in touch with me. Spoken to Damien George, the creator, Matt Trentini, and Jamo, all the people who are on the Discord community. And if you've got any kind of problems, they jump on that and try and get you the help. So a very, very strong community out there. So I would say there is also probably a lot more. This is not scientific when I say this. This is more of my opinion. There seems to be a lot more libraries, frameworks, community engagement around MicroPython than there is in Rust. But I'm coming as an existing MicroPython user. I've not really seen a lot of the Rust community, the frameworks, the libraries, I've not come across them yet, so it's difficult to judge that. So for me, I'm kind of biased on that way. I would say that the community for MicroPython is stronger and larger, but it's probably a smaller group because it's specific to microcontrollers. So learning curve and developer experience. So Rust definitely has a steeper learning curve due to these unique concepts like ownership and lifetimes. You will have to go through the Rust language tutorial, and there is a book, the Rust book, to get up to speed on how to use it. MicroPython, if you've used Python, it's very, very similar. There's very little differences. The differences really are just to do with the input and outputs on MicroPython. So if you want to do something like make a servo move or switch an LED on and off, you just need to know what pins are connected to on the actual controller itself and expose them through the machine.pin library. So that's really the only learning curve in MicroPython over Python, and it's definitely a lot easier to get up and running with MicroPython. This is due to the tooling, because the tooling is designed for you getting code on your microcontrollers, and also the language lends itself to simplicity, just the way that it's structured. There's a lot less cruft, a lot less curly braces, semicolons, all that kind of stuff in Python, and the only difference really is that Python has these indentations in your code blocks to define blocks of code, whereas in Rust, in Rust and in C, you'll have to have these curly braces to define blocks of code. So a white space doesn't matter, you can have it structured however you like. That can mean that code looks a lot messier. So one programmer might be very messy in Rust, whereas another person might be very structured. In MicroPython, the structure of Python, the language, means that all code will be indented the same way. So it's going to look the same whoever programs it from that kind of visual perspective. So yeah, developer experience, I would say MicroPython is easier to get up and running with code. Excuse me, this is me drinking too much Diet Pepsi. And Rust, there's a steeper learning curve, but once you've got there, I think it's probably, it's as fast as any other language. There's probably a lot more to do to make a simple program though. We'll have a look at an example of how to switch an LED on and off in MicroPython versus Rust. And I was quite surprised, how many is it, 300 lines of code to do that in Rust, whereas it's just a couple of lines in MicroPython. Again, that's probably because it's designed for microcontrollers. Safety and reliability. So when we talk about safety, we mean about making sure errors don't creep into our code. So Rust has a very strong emphasis on compile time error checking and safety guarantees. So when you write a piece of code in Rust, the compiler will make sure that that's a reliable piece of code. It can look at, if you have a variable and you define that as an integer, you can only store integers in there. The compiler is basically going to stop and say this code is not correct. Or if you create a variable and you don't assign it a value, the compiler can say there's a warning here, you've created a variable but you've actually not used it. So it's very, very good at detecting errors and telling you how to correct them. MicroPython also does do that to a degree, or Visual Studio Code with the if you've got the right extensions in there, can detect those kinds of errors as well. But MicroPython and Python are dynamically typed, so that means that you can assign a variable one value. So you could assign the variable x value 1, and then later down in your code you could change your mind and say x is now equal to a floating point number or a string or an entirely different class. So because it's dynamically typed, that type can change. And that might be considered by some people from a C or Rust perspective as like very bad programming practice, because if you change the type midway through your program, you're introducing a vector for errors to occur. So MicroPython focuses on simplicity over strict safety checks. That makes it a lot easier for people who are coming to this new, because they don't have to worry about types and things. It can be inferred for the value that is passed to it. So Rust is designed to make very robust code. MicroPython is designed to get you up and running very quickly on microcontrollers, and particularly with an emphasis for beginners. So yeah, I don't know who wins that particular round there. So I would say MicroPython is definitely quicker to develop with. Types are dynamic but can lead to errors. So it's kind of on the responsibility of the programmer to make sure that that doesn't happen. Rust is very fast, however the develop environment and workflow is still immature compared to MicroPython in the sort of embedded environment space. So it's not really designed for embedded devices, even though the code that it creates is very efficient. So compile time errors, I've had lots of compile errors when I was trying to do even the most basic Rust program. So I was trying to get this blinking lights program to work on the Pico W, and I think I had 150 errors. And this was from code that was supposed to work from somebody who'd been working on this already. So yeah, you can see the blinking lights code there. I say it's 300 lines of code. So it's not particularly suited for internet development yet, Internet of Things development. I say yet because it might come in time, but for me, it really isn't a starter for 10. And the whole life cycle of how you get code onto your microcontroller, not very straightforward. But I would definitely encourage you to try both, and let me know what your thoughts are on that. Even give me advice if you think that there's something I'm missing here. If there's a particular plugin I need for Visual Studio Code, definitely let me know what that is. But my experience wasn't great with Rust to begin with. So if you like what I do and you want me to make more kinds of videos like this, please give this video a like. Drop me a comment, let me know if you have a preferred programming language. Is it Arduino? Is it Java? Is it Python? Is it MicroPython? Is it Rust? Let me know in the comments below. Let me know why as well. And if you haven't already subscribed to this channel, please consider subscribing. It means an awful lot to me if you subscribe. It helps the channel algorithm know that this is a good channel and other people will be able to find it as well. Okay, and I do go live every single Sunday at 7 o'clock GMT. I think we're going to be changing over at the end of the month. We're in March at the moment as I record this, 10th of March. So at the end of the month, I think we change over to a British summertime, BST. So it just shifts by an hour, a bit like daylight savings in the US, but we do it a little bit later on, I guess. Okay, let's have a bit of a demo on Rust, shall we? I'm just going to pull up my notes on another screen, and then I will get over to Visual Studio Code, and we'll create some code. Okay, so let me get over to Visual Studio Code. I'm just going to adjust my screen a little bit here so we can see what's going on, and then we're going to create some code. So let me just clear that screen. Let me make everything a little bit bigger so we can see. And what we will do is we will just back out of this. Right, so I'm just going to hide that folder for now. And so I've got this screen kind of split into two parts here. The top over here is where we're going to write some code, and the bottom down here is just like a terminal window. So the first thing I'm going to do is I'm going to create a new project. So we use the cargo tool to do this. I'll show you how to install Rust in a second, but I just want to show you very quickly how we would create a new project. So if I do cargo new, and then let's call this a live stream demo. So that's going to create a new kind of workspace for our package. So we can now change directory into this live stream demo. And if we now actually open up Visual Studio environment, and let's just close that window there, and let's have a look what we've got. We've got this live stream demo folder that's been created for us, and there's three things that it's created for us automatically. There's a source folder with a main.rs. So .rs is the Rust file extension. We've got a .gitignore, which is for ignoring any folders that we don't want to have in our Git repository, so it's kind of designed with Git in mind. And we've got this cargo.toml. So toml is a format for storing configuration files in. So I'll just move this little invisible window that you can't see out the way there. So we can see there it's got package, name is livestream demo, version is 1. So we've got the minor version, major version, and the kind of bug fix version, and the edition 2001. That's weird. And then it's got some, for more keys in their definitions, go to docs.rustlang.org, cargo reference, blah, blah, blah. So let's do that right now. What I'm going to do, I'm just going to open up the Rust, let me just find that, rust.lang, here we go. So go to rust-lang.org. This is the official website of the Rust Foundation, and you can see on here we've got install, learn, playground. I would definitely say check out the playground area. On here we have an area where we can actually try out code and have a play with it. So you can see there's a bit of an example already. It's a little bit like a Jupyter notebook, but I guess a lot simpler. And now there is also this documents, doc.rustlang.org, and this is the Rust book. So you can basically start from here and work your way through how to install Rust and things like that. So there's a very simple command that you can grab. So in fact, there's a little button there you can click on. You can copy that. If you're using a Unix system, you can basically just paste this in, and this shell script will install everything that you need for your system. So that whether that's like a Linux or Mac OS. There is also a Windows version as well, so you can click on these links here. Hopefully you can see that Rust Lang tools install, and there's also the Visual Studio 2022 plugins and so on. So once you've installed that, you can do this Rust C version. So if I go back to here and I go back to, so I'm just slightly in the way there. What I'm going to do is just pull this window up a little bit here. So if I do Rust C -- version, you'll be able to see what version. It always seems to take ages to do this, whatever programming language you're using. So you got 1.74.0, and that's the 2023 November the 13th version, and it's installed via Homebrew because I'm using a Mac on here. So that's just for reference for future people, if you were interested to know what version I was running on here. Okay, so we've got Rust installed on my computer. We've had a look at the website. So let's create this hello world. I just did one for the live stream demo. This is going to be our hello world program. So I'm going to go into the source folder. I'm going to open up this main.rs, and they've already provided this as a working example, interestingly. So let's have a look at this code. We've got fn. Let me just make this a bit smaller here so we're not getting too distracted by that. So fn is function. It's a bit like def in MicroPython. We've got the name of the function, the curly braces, and then you've got these, well, they're regular brackets, I guess. These are the curly braces. That defines the block of code. So the convention is you have the first one on the line of the function name, and the last one is kind of on a new line itself. But this is like C, white space doesn't matter. You can have this however you like. You could have all that on one line if you really wanted to. Then we've got print line and a little exclamation mark, and then hello world. And then we've got the semicolon at the end. So this is like C or the Arduino language, very, very similar like that. And to get this up and running, let's just clear the little terminal down here. We could do a number of different ways of compiling our code. So we can just do rust C and then the name of the code, which is main.rs. And it says there is an error there. What's the error? Couldn't find it. So I'm not in the actual source folder, that's why. So let me just... there it is. So let's try that again. Rust C main.rs. If I now do ls to look now, I've now got another little file that's appeared, main. And if I just do like the long version, of list, we can see how big that file is. So it's 400k to do hello world, which seems to me a little bit excessive. We'll look how big the C version of that is in a second. So let's us run this. So if I do ./main, this will actually run the code itself. So there you go, hello world. So that's all our program does, it just prints it out. Now, Dale's just commented in the comments on the live stream here, something I was going to bring up, which is, what's that little exclamation mark there? So that means that this is actually running a macro rather than a function. So printline is a built-in macro within Rust. We didn't need to import anything into our code and include anything like you do in C or Arduino. This is something that's built into the compiler. It already knows about this. So we use this exclamation when we're using macro code rather than functions. So printline is actually a macro rather than a function. The difference at this point, we don't need to get into that, but there is a nuanced difference there. Okay, so we've created our code. So let's do something else now. Let's assign some values. So if I come over here and let's assign a variable a value. So in Rust, we use the let statement. That means that we're going to create a variable. We can say let x equal 10. For example, and then semicolon. Now let's compile this and see what happens. We can just do rust C on there. Let's see if it generates any interesting messages. It doesn't. That's valid code. But what is x? We can just leave it a bit like Python. Let it guess what that value is, what type of variable it is. But it's better and a better practice to actually say what that is by defining the type. So if we say this is an integer, it's a 32-bit integer, i32 is the type of variable. So a bit like if we did this in MicroPython, that would be int. We would just say that's an int. So by providing the type, we're creating better code in effect. Now the other thing about this is x is actually immutable. We cannot change the value of x now that we've defined it. If we want to change the value of it, we have to say that it's mutable. So if we say let y be mutable, and we can do the same kind of thing there, that means we can change the value of that. So if we come down here, let's get rid of well, let's try and change the value of x, for example. So if we say x equals 20, and let's see what happens if we try and compile that code now. So it's actually let me change the value of x, which I didn't think you could do. I thought the whole point of that was that it was immutable. So let's try changing the value of y and see if that still compiles. So yeah, I'm not sure why that actually didn't generate an error there, but that's interesting that was the case. Now I'm currently using rust C there to compile the code. You can actually do cargo run instead, and that will build in any dependencies. Now we haven't actually included any dependencies yet. We'll do that in a second for a little program that we'll use to guess the number. But we could do cargo run main, and you can see there it says compiling, finished, and running. So it's actually run the code there. So it's done the whole like loop of compiling it and running it. So a lot of people use cargo run rather than just compiling it and then running the code manually from the command line. So that's why cargo is pretty cool as a tool. So that's let's have a look what else we have. We could also do a string. So let's come over here and say let's call this guess. We'll make it mutable as well. Let guess equal a string new. So this is where, again, if you've not used Rust before, what are these like double colons? That's a bit like when we import something in MicroPython and we use the dot to bring it in, we're actually defining like a library and then the function within the library. So that's kind of what's happening there. So that will actually let us create a string which is guess. And what we now need to look at is let's do some comments. Just like in C, we can do 2 double slashes like so. That's for a single inline comment. Let's see if we can do some comments. I think that's as much as I know about how to do comments in Rust. I'm pretty sure you can do like a block of code, a block of comments rather than just the single line ones. Yeah, in C it's /* star, isn't it? There we go. So this is a like that. So we can do multiple line comments just using the /* star. That's just like C, similar to how you could do it in Arduino as well. And yes, we've talked about functions. So if we want to create our own function, so rather than just using this main, Rust always has a main function. It doesn't work without that. So if we want to have something up here, so let's say print _message. Let's just have in there a variable which is message, and that's going to be a string. So how do we do that again? So it's string message equals, sorry. I think that's how we do it. And then we have the curly braces as well. So there we go. We can just have a bit like how we do in print statements in MicroPython. We can just do print the message like message is, and then we can just have the actual message after the comma there. So if we come over here now, we just print out, instead of hello world, we could actually call our function, which was print message, and then hello world. So let's compile that and see how bad my Rust code is. So there we go. And if we change that message to be hello subscribers, and then run that again. Oops, did I not build that? And run. Let's try just doing Rust C main. There we go. So that'll be to do with how I've defined that that string there. So I just need to have a quick look at my code to see what else I need to do on there to get that working. So I'm basically just going to leave that out. Actually, ignore the function up there with the string bit. That isn't how you do it. So I'm not the world's best Rust. There we go. If I do that, that should work. Let's try that. No, it's not happy with that. Okay, so what I'm kind of going off script a little bit here, so I want to go back to my my notes here. So one of the other things that we can do with Rust, we can have targets. So instead of just compiling to whatever platform or architecture you're using, you can compile for a completely different architecture, such as Arduino, ATmega 328P, or the RP2040 from Raspberry Pi, and that's how we will actually generate code and then transfer it onto our Pico. So what I want to do though next is just show you another, let's just create another piece of another package. So I'm going to come back out of there. I'm going to do cargo new, and then let's call this guessing game. Oops, new, sorry, not no. And that's created that new guessing game. So let's go into there, cd guessing game. So yeah, we've got the usual kind of thing, and then let's just go into here, guessing game. You can see I've been testing this beforehand. Let's go into our source code, and again, it always has this main dot hello world thing as just an example when you use cargo. So we're going to change that to be the guessing game, and this is from the tutorial. If you go to the website we looked at a second ago on Rust Lang, into the docs area, they've got this tutorial about like a guessing game. So we'll do a little bit of it today, not the whole thing though. Guess the number. So that's just going to print that out, and then we want to have another one, so another print line. Please input your guess. And then we're going to have a variable called guess, so let mute guess equal string new. Now the thing that I was missing before in my code when I was trying to use string is we need to import string from the standard IO. So this is how we import libraries. So use standard and then : IO. That will bring in all the functions that are available to us from the standard IO library. So that's string is one of those. That's why it wasn't working before. Okay, and then we're going to basically just print out. So IO standard in, and we've got two lines there. So read line, that's going to read in from the keyboard somebody's number, and let me just change that to be a guess with two S's. This is just a Visual Studio Code. Yep, you can install that, that's fine. And so there's two parts to this, read line guess and mute guess. So what's going on here, and mute is we're passing in a reference, that's what the ampersand means, and the variable that we want to pass in the value of, or the reference of, is guess. So that's that variable that we created there. And then we're actually saying that we expect it to be a string. If it isn't a string, we can say fail to read the line. So if the user passes in anything other than a string, it's going to generate that message. Now we could simply have this dot right up against the function name there. We could also have that right up against it, so that this linter thing is kind of getting in the way a bit of making it easier to read code, but that really doesn't read very easily. So the convention is, if you've got a dot, you can basically just put that on a new line, because white space doesn't matter in Rust. Okay, and then finally we just need to print out the result from this, so we can just do a print line at the end of this. So print line with the exclamation mark, and we simply just say on there, you guessed, and then the guess. Right, let's compile this and see what happens. So let's do Rust C, and then main, like so. So we're not in the source folder again, gotta get used to doing that. There we go. Is it rust.rs? Let's try that. Okay, so we've now got main. If we now do main, saying hello, what have I done wrong there? Do I need to save that? Is that why that didn't happen? And let's run that. There we go. So please guess input number. I'm going to say 10, and it said you guessed 10. So it's not actually comparing it against anything. In the example on the Rust language website, they show you how to build a little game where you can actually have a random number generated, and then it compares if it's higher, lower, or if you've won by guessing the number. So it's kind of like a fun little game, but it's quite complicated to do that in Rust. So what I want to do next then is show you the comparison between writing a program in Python, in C and in Rust, and then comparing the output sizes of the code that's generated. I thought this would be quite an interesting exercise to do. So what I'm going to do is I'm just going to create under the same source folder here. I'm going to create a new file. I'm going to call this one hello c.c. And in here, we're going to create a C program. So let's just import, sorry, it's include, isn't it, in standard io.h. That's the header file for all the standard input output stuff. And then, yeah, we're going to do an input int main, which is it returns a value that's an integer. Main is the name of the function. We have the curly braces just like we have in Rust. We have printf, which is how we print things to the console, and then hello world, and then this /n means put a new line after you've printed this out, just so that in the console it returns a little console character after that. Return 0 just means everything's worked fine, there's no errors. So what I'm going to do now down here, if I now compile this with the GNU C compiler. So let's compile hello c.c. Let's just move this a bit higher so you can see what I'm typing there. And we can say that the output is just called hello. Right, what have I done wrong there? So let me just have a quick peep. Sorry about that. So let me just have a quick look at the code that I've got there. So include standard io.h, int main. That should compile fine. Yeah, I don't know what it's complaining about there. I'm just going to exclude the output thing and just see if that will compile. No, it's really not happy with that. Initial undefined. So is it that include? I'm not sure why that's not working. I'm not a massive C programmer. Let's just save that. And let's try that again. Oh, there we go. I had not saved the file, for goodness sake. Right, let's just output that as hello C. Okay, so we can just remove that a.out. That's what it calls it if you don't actually provide an output of the file. And then let's just run this. So we have hello C. If I do /hello C, it says hello world. Now if I do ls-l, we can see that the output size, the size of the file that's been generated in C, let's just move this up here so you can see, is 33k. So it's not very big, just to generate hello world. Let's do this now in MicroPython or in Python. Let's just create a hello.py. And this is simply going to be print. Oops. So all this help is really not helping there. There we go. Hello world. No, I don't want the guessing game. I just want hello world. There we go. So we don't need to import anything. We can just do one line of code. We save that now. We come down here. We look. It's 22 bytes for the hello world program in Python. And if we do, we can do Python 3 and then hello.py. It'll do hello world. So Python files, because it's just pure text, it's just a script, are tiny, absolutely minute. And this is great if you're working on a microcontroller because your source code is really, really small. It's probably going to be smaller than the actual generated code. Let's do the same in Rust. Let's go back to our main.rust and we can get rid of everything that we don't need in there. So let's get rid of all of that. Let's basically just have the hello world as the main part. And let's just change that guess the number to be hello world, like so. We can get rid of the use standard IO, we don't need that. Let's save that. That was the thing I did wrong last time. And now let's just do rust c main.rs again. And if we now just look at the file sizes, look how big the main, which is the Rust program, 492k. So it's massive. Python/MicroPython 22 bytes. The C program is 33K and 492 for the Rust. So Rust might be really, really fast at running, but it creates huge files, is for even the most simplest thing. So again, we can just do that main to run the Hello World program there. So when we talk about efficiency, there's efficiency of the code that runs, and there's efficiency of the programmer who's creating the code and how simple that is. So we compare the three different programs there in C. Let's try to grab the window there, and I can't see the, there we go. Yeah, we could probably just grab all these side by side. Let's just split the program there, and then that one as well. Let's have 3. So that's the Rust code, that is the C code, and then we can just change this to be the MicroPython code, if I can just find that, hello.py. So yeah, when I talk about cruft, this is what I mean. The Python code is basically just one single line, and it just has the print command, the brackets, the speech marks we include to wrap around the text string, and that's it. In C, we have to include standard I/O because obviously it depends on what you're generating. You might not need standard I/O because you might not be writing to the console if it's just an embedded system. But we're bringing that in. We have to have an int main because the code has to know where to start. And then we have to have printf to actually have the hello world. Now we could actually have void main, which means that there is no value, in which case we don't have to have that return 0. Not sure how much difference that makes to the code that outputs. Let's just compile that and see. If I just do the GCC, let's just find the code for that. There we go. Oops. GCC hello C.c output to hello C, and let's have a look if there's any difference there. So let's just find that hello C. So it's 33K as opposed to what it was before, which was, yeah, 33. It's the same size, so it makes no difference whether we include that return or not. But again, it's 5 lines of code versus the 1, whereas Rust has got 3 lines of code, function main, print line, and that's it. I guess there's an extra line we didn't need there. So yeah, we've just got a little extra step in C, but the code is tiny and it's very, very fast. Now we could, if we wanted to, have timers around these pieces of code to see how fast they are actually executing, and C is going to be the fastest, Rust is then going to be next, and then it's going to be MicroPython probably 10 times slower because it's running in an interpreted environment. Okay, so let's have a look what else we need to cover off on here. So we talked about the complexity of the code, how fast it is to write the code. I would say MicroPython/Python is the fastest because you've not got all these curly braces and semicolons and things at the end. It's easier to read because you've just got less code to visually consume. There's less cruft, like all the curly braces. So it's just easier for a developer to develop stuff. Let me see if there's anything else I wanted to cover off. Yes, there was. So we've not really used any dependencies in our code other than the standard I/O, and this cargo.toml file is where we define. Let me just close out these other windows so we can see what's going on here. Basically, I just want to grab that, just have it in there, and let's just close out those. There we go. So this cargo.toml defines the package. So if we're creating like a block of code, a library of code, and we want to share this with other people, we might want to version control that, and we can do this through this cargo.toml file. We haven't got dependencies in there, so that's fine. But if we did have dependencies, we could essentially lock the dependencies, the version, in this cargo.lock. So this is package live demo, and the version is 01.0. If we generate some other code and it's like version 2, we can actually lock the version to the code that we've written so that we know this is like a known good version. Even if newer versions come out, this is the one that we know works well. And it's a bit like a requirements.txt file if you're using a virtual environment in Python, but it's kind of nicely managed because requirements.txt is a text file that you have to manually create, whereas the cargo will create these toml and the lock files for you as you change your code, which is pretty good. And what we can also do with cargo is we can update any dependencies that we have. So I think you can define something in here. We'd have to go back to the language definition on here. So let me just find in here. It does talk about the different versioning of things in here. So I just want to find an example that we can include in here, just to show you what I'm talking about. So I'm just trying to find if they've got one to hand, but they haven't got one. So they call them crates as well. So if you, what we would call something like a Python module library, they're called crates in Rust. I was just trying to find if there's an example one that I could show you how we can update the versions, but essentially Cargo can help us maintain the versions, and you would simply come down to your terminal. If I just move all this stuff out of the way, bring this up to the full screen so we can see what's going on. We just clear the terminal, and you can just back out of that. If we did Cargo update, it would check to see if there's a new version of the dependency. If you've got this off the internet, like a repository, it can check the repository for the latest version and then apply the update to your code. So it's pretty cool that it can do all that. Okay, let me see if there's anything else I wanted to cover off on my notes. I think that was pretty much it. Yep, so let's get back to our slides. Cool. So that's my quick and dirty demo of Rust. I've not been spending very much time learning the language yet, but I will probably have come back to this and have another bit of a play. I certainly want to get the code up and running on a Raspberry Pi Pico. So what I can show you, if I go back to the website for a minute, somebody has created a really great resource, and I've actually included a link to this in the show description today. So this is Getting Started with Rust on Raspberry Pi Pico. This is by Jim Hoddap. And if we scroll down a little bit, I can show you the kind of complexity of the workflow of getting code onto your Pico. So first of all, you need to have two. You need to have one that can upload the code to the other one. And you can see that it's using the read and the RX and TX, so the read and write transmit lines. And it's also got some debug lines there as well, so it can actually receive debug information from the Pico. And we've basically just got some power going to that as well. There's a sort of image of how you would wire this up as well. So that's how you would essentially wire everything up. I'm just going to quickly scroll through this, and then we need to bring in this multi-architecture component so that we can output code to the RP2040. If you're using a Mac, you need to install Rosetta, because this is Intel code running on an ARM processor. So that just adds an extra level of complexity if you're on a Mac. And then you need to install all these different libraries. So it's quite complicated just to build a build environment. So you can see there all the different things that we need to do. Once we've done that, if you've got Pico Probe as well, this can help you debug the firmware. So this is the official Raspberry Pi debug probe that they sell. What else have we got? And then you install Rust using the script that we looked at before. Then create a new Rust environment, and then you need to create this this file here. So this is simply blinks the LED on board. So look how complicated this code is. This is not designed for beginners, is it? This is something for people. It's very, very close to the hardware. It's more like programming in C than it is programming something like Python. So yeah, quite complicated, and you really have to know the hardware, whereas a lot of that's abstracted in MicroPython. So I find that easier to comprehend and easier to use. So there you go. That's how you go about doing it. It's pretty complex. There we go. So I'll put a link to that in the show description if you want to know how to do that and have a play yourself. I couldn't get the example code from this to work. It had 150 error messages or 300 error messages. I don't even know where to start to debug that. It might have been just one thing that's wrong, like a one dependency, but yeah, I don't know how to do that yet. So I just wanted to show you that. Cool. Okay, so last week I said I was going to build 4 projects in the week off that I had from work. So I want to give you an update on where these are all up to. So the first one was the electronic trombone, which is essentially a ultrasonic rangefinder, which I have on my desk somewhere, and it will have one of these. This is from Monk Makes, a little anemometer, so you can blow into this, and depending on how hard you blow, it'll spin round and it will generate a voltage, and you can measure that voltage because it's less than 3 volts to basically define how fast this is turning, and therefore we can define how hard the note should play on our little electronic trombone. Now I can actually show you the design of this because I have designed it, I've just not 3D printed it yet. So let me just grab a Fusion 360 and open it up, and I can show you a bit of the example of how that's working. Just take a moment or two for Fusion 360 to load up. I've also been working on the long bell orchestra, so I've got a whole bunch of copper chrome-plated copper pipes. I've simply sliced these off. They was 2 meters long when I grabbed this from the local DIY store. So I've got just where Alex normally sits, there's a chop saw there. So I've chopped these in half, and then I've drilled a little hole through the middle there, and I've got a piece of string. And what we can do with this, if I just grab something that's let's grab this, it can make a sound depending on the length of the tube. So it's got a really nice sort of bell sound to it. So depending on the length of these, we can define an entire octave. So I've got all the rest of the tubes there. I've got 12 of them in total. The thing I'm a little bit nervous about, because these weren't cheap, I think they were about £26 each or something. It was like very expensive to get 6 of these. So once you've removed the metal, it's gone. So you've got to get it right. And essentially you have to, is it 12 to the square root 2 or something like that? I don't know. You basically, there's a formula, you slice the tubes up into 12ths essentially, and each note is just 1/12 less than the previous one. So we can create an entire octave of sounds of bells, and we can have something like this, which I've 3D printed with 12 servos on it. I could probably get away with having 6 servos, 3 servos per side, 1 in between, and depending which way it goes, it can hit one bell or the other, or you could just have 1 for each of them. So this is what I'm intending to do here. And I've also got, let's grab this Pimoroni Yukon board, and I've got a whole bunch of servo, if I can get that into focus, if I just hide my face it'll focus there, quad servo regulated and quad servo direct. So there is 4 on each of these modules, and I've got 4 modules, which means I can have potentially 16 servos being controlled by this Yukon board. Now the Yukon board doesn't have Wi-Fi built in, so we'll probably have to connect by one of the connectors on here to maybe one of the custom modules and talk over UART to communicate with a device, for example. But it's got all the nice hardware and all the voltage regulation and everything we need to power these servos. So the idea is this servo can sit here, the bells can sit inside here, and the servo can hit it. So one of the things I've not designed yet is the hammer that will hit the bell, and I'm not sure whether there's enough force in this little servo arm, to hit the bell with sufficient force to make a nice note. It might just click against it, which isn't great. So let's go over to Fusion 360, and I'll show you some of the designs that I've been working on there. So let me show you first of all that long bell orchestra. So if I come over here, oops. Let me just grab the Fusion. Why is it not? Let me just try that again on that. So there we go. Oops. There we go. So this is the long bell orchestra. You can see there we have all the servos and the different lengths of pipe, and they're basically going to sit next to them, and the little servo horn will hit each bell. So they're all lined up nicely so that they will move from one direction to the side of the bell. Again, I'm not sure if that's going to be enough. The only way to find out is to build the thing and try it. So that's the long bell orchestra. Let's try the electronic trombone next. Yeah, I had to model the fan to get this to work as well. So I've got this first piece of 3D printed thing here. You essentially hold that. If I just jump back here, I'm not sure why it keeps going to the Chrome there. Let me just hide Chrome. I can't even see Chrome on the screen actually, which is weird. There we go. Sorry. There we go. Right. So yes, this first piece here, you would essentially hold with one hand, and that's going to help you define the distance between the ultrasonic rangefinder. So it's essentially just like a reflector, really. Then we've got the ultrasonic rangefinder there pointing at the little reflector. We've got the Pico on the side there, and we've got the fan. And they're all the parts that we need. We'll also need some connectivity, and I was thinking rather than having this work over Wi-Fi and all the complexity of getting MIDI to work over that, we could probably just use CircuitPython and connect a cable to this just to make it a little bit simple. So I've not written the code for this yet, but I have designed this. I've even got like the little motion study thing, so we can animate that joint that's in there. I don't know if I open this up, is that going to work? Let's open that up, and if I just click on run, you can see the little fan spins around there. You can just do that. So that's kind of how it's going to work. As you blow into this, it'll turn the fan around. That will define the volume of the note that you're playing, and the distance between the rangefinder and the reflector will give you the pitch of the note. So we have done something similar like that before, as I discussed last week. So not 3D printed that one yet. It should be quite a quick print. These are quite small things to do, and we can probably print these optimally, just lay down, whereas this one, not sure the best way of printing that, because maybe print that upside down with the long part pointing up perhaps. So that's the electronic trombone. Then we have the robotic arm, so the motion controlled arm. So this is why I spent a lot of time not actually making the thing but designing it, because this was quite a complicated thing to design. So this is the robotic arm, and all the parts you can see there are articulated, and I've made a good start on printing all the parts out here. So this is the base. I'll just grab that there. So the idea of this is this can be bolted to a desk. There's a great big 3mm3 hole there, so you could have this on your desk. This would go down under the desk, and you could basically clamp it in place. And I've got these NEMA 17 stepper motors. These are going to provide sufficient sort of power to turn the whole arm. When the robot arm isn't having any power, they are completely limp, so I might have to redesign this to use something like a worm drive perhaps instead. That's the only thing I was thinking maybe is a bit of a misstep. And I've got some other parts here which I've already printed out, so this effectively will attach to the base there, provide it can turn that way, and this one can turn that way. And I'm going to have another set of these on top. In fact, here's one I've not... I've 3D printed it. You can see all the support material there. I just haven't removed that yet. So that can essentially bolt to that piece there. So I've printed these in small sections that are easier to 3D print. Bolt it and glue it together to make the... so two of these make an arm section, and they would each have these sort of elbow pieces on there. So there'll be two of these to give it the full kind of effect there. So if I go back to... you can see there's one piece I printed here, there's the base, there's another piece, and then there's the sort of end which will have the camera attached to it. So yeah, there's a lot of weight in there. These NEMA 17 motors are pretty hefty, so there's a lot of force being applied to that bottom there, and also to that joint there particularly, because that's having to hold everything up. I'm not sure if I've got the... well, you can see it on here actually. So the way that these are actually attached in, there's a little connector there, and it's got a little screw thread, and that attaches onto the NEMA motor there. I haven't got any bearings on here, so one of the thoughts I've had about this is maybe I need to have some bearings that can take some of the load and spread it across the arm rather than it all being on that one NEMA motor there. So that's the robotic arm. The robotic arm is also, I've been talking to VM, who, as you know, one of the robotics software companies based in New York. They've taken an interest in this robotic arm, so I'll be working with VM. They were actually going to help sponsor the build of that, any parts that I need, and we're going to be making this work with inverse kinematics, so we can move that endpoint of the camera or whatever we've got on there. That could be a microphone, a light, whatever we like. Using inverse kinematics, we can control that. So rather than it just being like a dolly track where the camera moves around the product. We can have our robot arm move in any orientation that we like. It could even have a microphone that when I move away from the microphone like this and my voice changes in volume, we could have the robot arm follow my voice by tracking my face, for example. So we can put a Raspberry Pi camera on the end is what I'm thinking there. So that's the robotic arm. That's kind of work in progress. And then finally the giant Etch-a-Sketch. So I've actually not done anything on that one at all yet. So the giant Etch-a-Sketch, I need to work on that one. That one is also been quite a fun one. I was thinking we could make that also like a remote thing where people can, from the kevsrobots.com website, they can access that. So that's one of the things I want to work on next. Cool. So a couple of other things I want to cover off as well. I've also created a Rust course on kevsrobots.com. So if I go over to kevsrobots.com and we go to free courses, you can now see that there is a Rust course on here, and you can basically just pick up some basics of Rust. I think it probably needs a little bit more work, this one. I just wanted to make notes about Rust as I was learning it myself. So some of the differences between Python and Rust are on here. But yeah, you basically just check that out. Thank you for that. You basically just check that out. Go to kevsrobots.com/learn/Rust to access that free course. I've also put a bunch of other articles on Kev's Robots as well. So if I go to the blog, you can see, let's go to the all blog. I realised I'd not actually documented the TheraPi MIDI instrument, which I developed quite a while ago. So there's a video on that one, and there's also now a write-up of how you can get all the parts you need and do that yourself. That's basically what the trombone, the electronic trombone, is based upon. This used a Raspberry Pi Zero. We're going to be using a Raspberry Pi Pico instead. And then we've got the motion control arm. So that's kind of work in progress in the electronic trombone as well. I also documented the Pico Tico, which I haven't documented. That's basically what that whiteboard, the giant whiteboard, is going to be based on. The similar version of that, just much larger. Cool. So that's I think everything I wanted to cover off on the project update. Cool. So yeah, if you want to check out kevsrobots.com/learn/, you can see all the courses there for free. There's a one, like I said, just been released on Rust, so definitely check that out. And we have merch. If you want to get yourself one of these amazing hats, they get talked about for various different reasons. Definitely get yourself one of these. I know a couple of people bought them last week, so thank you for that. And if you've not joined our Discord server, definitely, if you've got any questions about projects or anything, this is the place to get the answers for this. Don't message me on social media. I probably will have time to respond to that. But I definitely go into the Discord group and ask any questions you like there. You can @ me in there and I will definitely get back to you on that. So kevsrobots.com/discord to get a sign up link for that. And I'm on social media. You can follow me on Threads at Kevin McAleer at threads.net. I'm on TikTok on Kevin McAleer 6, on Instagram at Kevin McAleer, on X at KevsMac, on Mastodon Social at KevsMac at Mastodon Social, and I'm also on Blue Sky at kevsmac.psky.social as well. And if you want to get your name in the credits, you can do this in a number of different ways. You can go to kevsrobots.com/coffee. You can do a super thanks, which is if you're watching this on replay. If you're watching this live now, you can do a super chat. I'll make sure that's enabled on the overlays just there. There we go. And you can also join the YouTube membership program just by clicking the join button that appears if you're watching this. I'm not sure you can do that from an Apple device because of the weird licensing thing that Apple and YouTube, you basically have to pay extra through Apple to do that. So I think they've just removed that button. But if you're doing this from the web, you can basically just click that join button there as well. Okay, I think that is pretty much everything. We just need to cover off some of the people who have supported me already. So let's call those people out. So last week, Mark Lewis bought me a coffee. Thank you very much for that, Mark. And to Alex, just Alex as well as Nicholas Han. And we've got a couple of members on the Buy Me a Coffee. We've got Lee, we've got Alvaro, we've got Maria Louise Mayer, we have Jeff Johnson. Hey Jeff, I know you're on the live stream today. We've got Dean Corty, Marlene Brent, Tom Shemi and Steve Phillips. And then on the YouTube membership side, we've got Dale, we've got Bill Hoy, Warren Steele, Stephen Cross, Jonathan R, Orkshrad39, Vince, John Paul Jolly, Alistair Webb, Software, Cassie, Tinkering Rocks, JDM, Johnny Bates, Hans from Cheerlights, Michael, and of course we have Tom as well. Cool, so I think that's everything I've got for you today. So if you're watching this on replay, I'll say thank you so much for watching, and why not check out one of these other videos here that YouTube will show you, and that helps also with the algorithm and helps get other people to see this. So please check out one of these videos as well, and I shall see you next time.